Alright, so let's have a look at the June 2011 Applied Physics, so Unit 5, Section B. So let's start off with question 1. State the law of conservation of angular momentum. Okay, so this is a fairly straightforward definitions style question. So what we have is total angular momentum is conserved unless it's acted on by an external torque. So it's very similar to the linear momentum definition. So let's write that down. So total angular momentum of a system is conserved unless it is acted on by an external torque. Alrighty, that's the definition. You just need to know that. Okay, when a star undergoes a supernova explosion, the star's core collapses into a very much smaller diameter, forming an extremely dense neutron star. So we've got some data about the period of rotation and the radius, and you've got a new radius after the collapse. Got no mass is lost and it remains a sphere, and we've got the moment of inertia of a sphere of mass m and r is 0.4 mr squared. Explain why the period of rotation of the star decreases. So this is a conservation of momentum type thing, which you might have got from part A, because no external torque is acted. So we know that the angular momentum before is the same. So we know that I1 omega 1 is equal to I2 omega 2. And we know that omega is 2 pi over t, so that's another equation. So you know that I1 2 pi over t1 is equal to I2 2 pi over t2. So those cancel. So when we go from a larger radius to a smaller one, essentially what's happened is I2 is going to be smaller, which means the 1 over t2 has to be bigger, so if we rearrange this to make t2 the subject, it might be more helpful. So we've got I2 over I1, and that's dot t1. So because the radius of the first one is larger, the I1 is going to be bigger than I2, so this I2 over I1 is going to be less than 1, which means the time period is going to be smaller, T2 is going to be smaller than T1. So that's the logic to answer that question. So determine the period of rotation of the neutron star, giving your answer to a correct number of significant figures. So the first thing, so we had I2 over T2. So let's put some stuff in for that. So we know that we've got 0.4 mass is the same, so let's just call it an R1 squared over 0.4 m R2 squared times by 1 over T1. 2. So let's cancel some stuff and let's flip them over. So we know that T2 is going to be T1 multiplied by all of those 2 squared. So we have values for each of these things. So the time period was 3.8 times 10 to the 6 we need to multiply that by 1.2 times 10 to the 3 over 4.1 times 10 to the 7. That all squared, so let's type that in. So we've got 12 times 10 to the 3 divided by 4.1 times 10 to the power 7 squared times 3.8 times 10 to the power 6 gives you a time period of 0.32555 or 0.3322 significant figures, because the data in the question is 2 significant figures. Okay, so let's move on to the next question. Okay, some motor racing cars are fitted with a kinetic energy recovery system called KERS. So as you brake, you're transferring the kinetic energy, some into heat, but some also to accelerate the flywheel. When it needs to accelerate, the energy in the flywheel assists by providing extra power for the acceleration. Describe and explain some of the features of a flywheel. In order to store maximum energy, you should include consideration of the flywheel shape, the material from which it's made, and its design for high angular speeds. Okie dokes. So we've got a longer answer question. So we think about this. What we want to do is we want to be able to store maximum energy. So the energy stored in our flywheel is going to be given by this equation here. So this is the energy you can store. And so what we're going to want to do is essentially be able to either have high angular speed and also to have very high moment of inertia. So we're going to need strategies to increase this. So if we're looking at the things we're supposed to be talking about, we're supposed to talk about the shape of it, the material from which it's made, and a design for high speeds. So in order to increase the inertia, we want to use a high density material, because this is going to increase the mass, because remember, sum mr squared. So one way we can increase the inertia is by using a high density material, and we can also look at a material, or the shape actually. And what we want to do is distribute the mass far from the center of rotation. So if you think with like a wheel, for example, we'd have a hollow center and all the mass around the outside, kind of like a bike wheel does with spokes. And the reason you're doing is to just distribute the mass further from your center of rotation, which allows you to again increase the moment of inertia. If we want to increase the angular speed, what we want to do is have low friction, because obviously that's going to act against the motion. So we want something like we want to use some bearings, or we want to use some lubrication to lower the friction. So those are the things that we can look to increase to maximize the energy stored. However, there are some limitations, and that's why it's talking about design for high angular speeds. If we think about the force that's acting on the material, like this, if we get to high speeds, it's going to require have a large force acting on the wheel. So we're going to want a high tensile stress material, or high ultimate tensile stress material for high speeds, because if it's a low strength material, what's going to happen is the force is actually going to cause the material to fracture and break. So that's what we're kind of looking for in there. So in terms of the flywheel shape, which is the first point it wants, what we're looking at in terms of the shape is distributing the mass far from the center of rotation. in terms of the material, there's two parts there. So looking at the high density material and also high tensile stress, in order to give you high moment of inertia and allow high speeds respectively. And also in terms of design for high angular speeds, you're going to want a low friction material, and also this high tensile stress is to do with the design for high angular speeds as well. So those are the key features you'd be looking for in your flywheel. Okay, so the flywheel has a moment of inertia of 0.036, and we've got angular speed, and we've got the speed of the flywheel changing from 3100 in a time of 6.6. Calculate the energy transferred. So what we want to know is the change in energy, which is going to be half times by I, which is 0.036. So we want 6400 squared minus 3100 squared. This is going to be the energy transferred, so 64,000 squared minus 31,000 squared times 0.036 and divided by 2, and that gives you an answer of 564,300, or 5.6 times 10 to the 5 1, 2, 3, 4, 5. Yeah, 5 joules. And the average power, so power is going to be the change in energy over the time. So that all occurred over 60 seconds, so 564,300 divided by 6.6. And that gives you 8.6 times 10 to the 4 watts, two significant figures. So those are your final answers there. Calculate the decelerating torque on the flywheel, stating the appropriate unit. So the way I'd approach this, your torque is the inertia times the angular acceleration, and so that will be your 0.036 times by your final speed minus your initial speed over the time at which it took. So we're effectively using an angular Suvat equation, and it's a decelerating one, so we'll get rid of the negative sign later on. So 3100 minus 6400 divided by 6.6 times by 0.036 gives you minus 18 Newton meters. So the decelerating torque is 18 Newton meters. You could also use P is torque times angular speed and put the average angular speed in there as well. That would work too, but this is the way I would approach it. Calculate the number of revolutions. So what we're going to use 2 times T. So that's going to be 6400 plus 3100 divided by 2 times by 6.6. So let's calculate that. 6400 plus 3100 divided by 2 times by 6.6 gives you 31350 radians. So we divide that by 2 times pi would give you the number of revolutions. It comes out at 4989.507. So that's going to be 5.0 times 10 to the 3 revolutions there, once you give that to 2 sig figs. Okay, an ideal hot air engine, a fixed mass of air, is continuously taken through 4 processes: isothermal compression, constant volume heating, isothermal expansion, and cooling at a constant volume. So show that the temperature of air at point D is 500 Kelvin. So what we can do is essentially look from process, essentially using the ideal gas equation, we can probably solve this. So we know that pressure at A, volume at A, over the temperature at A must be equal to the pressure at D, volume at D, temperature at D. And I picked A because it's where we know all the information. So if we want the temperature at D, it's going to be the pressure at D, volume at D, temperature at A, over pressure at A, volume at A. And we know that the two volumes are the same because we can see that from the diagram, so we can get rid of those. So if we plug those numbers in, the pressure at D is 2.5 times 10 to the 5. Now the temperature at A is 300. No, this pressure at A is 1.5 times 10 to the 5, so those cancel too. And when you calculate that, 2.5 times 300 divided by 1.5, which is equal to 500k down there once you plug that in. So just using your ideal gas equation there, because we haven't changed the mass at any point as it tells you in the question. Apply the first law of thermodynamics to calculate the energy supplied by heat transfer process C to D. Okay, so first of all, let's state what the first law of thermodynamics is. So Q is going to be equal to the change in internal energy plus the work done by heat transfer. So from process C to D is an isothermal expansion. So if it's isothermal, that means that delta U is equal to 0. So we know that Q equals W. And we know that the work done is 173, so that must be 173 joules as well. Hang on, let's just check it was in joules, not power. Yeah, joules. Okay, so exactly the same number. Okay, the engine contains a device called a regenerator, which stores all the energy rejected by cooling in process D to A, and gives up all this energy to the air again in process B to C. This means that the energy must be supplied to air by heat transfer from external source only in process C to D. Calculate the net work out of the cycle. So we've got the total work we've put in is during process A to B, which is 104, and the total work we've got out of it, including all the heating and stuff, is 173. So that means the work during the cycle is going to be the difference between those. So it will be 173 minus 104, which is going to give you 69 joules. Show that the efficiency of the cycle is the same as the maximum possible efficiency of any heat engine operating between the same highest and lowest temperatures. So let's calculate the maximum efficiency. It's going to be the temperature difference over the hot temperature, which is 500, and then we're going to do 200 divided by 500, which gives you 0.4, and the efficiency here, the useful work out is 69, and the total put in must have been 273, and then so that's going to be 0.3998, which is approximately 0.4 as well. So in this one, I've had a few people in my class ask me about this one. This is the useful work you get out. This is the total you must put in, because you can't get essentially a total out more than you put in. So a few people have put 104 in. So this must have been the total amount of energy supplied. This is the useful work out, so it gives you the same efficiency there. On the axes below, sketch the cycle on a graph of volume against temperature. Label points A, B, C and D. So we've got two isothermal processes, so we're going to have two processes where the temperature is constant, so those are going to A, B and C and D. So we're going to have two processes like this, and the other process must connect those two, so you end up with essentially a box, and it's going to be going round like this. So the key here was putting in your isothermal processes. We know we've got the same change in volume, so we know they're the same height, which gives you two horizontal lines left over. Okay, several inventors have tried to build an engine that works on this cycle. Give two reasons why they have been unsuccessful. You can't. Constant volume is impossible. Impossible practically, and the reason for that, as engine would have to stop. To keep the volume the same, if you think the way the piston works, keep volume the same, the piston would have to stop, which means the whole engine would have to stop. So that's not possible. You would almost certainly be losing heat to surroundings, meaning your isothermal process. It just won't occur because the temperature would drop when you were supplying heat to the surroundings, so that would cause it to drop. An isothermal process is also impossible to have unless it's happening infinitely slowly or via a perfect conducting type material. A regenerator is going to be losing heat as well. You're going to need a very large surface area, which you don't want to have because it makes things big. There are loads of possible options here involved. Okay, a heat pump is used for heating a small workshop. The heat pump extracts energy from a patch of ground outside the workshop. The coefficient of performance of the heat pump is 3.2, and the average electrical power input is 780. So calculate rate at which energy is delivered to the workshop. So what we've got here is we've got the heat extracted from the ground. We're putting work in, and what we're trying to work out is what the Q in is. So the coefficient of performance is the useful energy transferred per 1 unit of work. So we know that Q in, which is the useful form in a heat pump, is going to be just 3.2 times 780, which is just 2,500 watts, or 2.5 times 10 to the 3 if you're being pernickety about sig figs. Calculate the rate at which energy is extracted from the ground. So Q out. Applying conservation of energy, it's going to be 2,500 minus 780, which gives you 1720 watts there. So this is where the diagram I've drawn above comes in handy. You can see which two add together. A student claims a heat pump delivers more energy than is supplied to it. Discuss this statement and explain why a heat pump does not contradict the law of conservation of energy or the second law of thermodynamics. Okay, so the key thing is what they're effectively saying is that Q out. Sorry, I'll crumbs. No, not Q out. Q in is greater than W. Is what essentially they're saying when they say it delivers more energy than is supplied to it. Just explain why a heat pump does not contradict the law of conservation of energy. So because Q in is equal to Q out plus W, that's your conservation of energy equation for this. You know that Q in is going to end up being greater than W because you've got the extra heat from the cold space. So we're essentially getting extra heat energy from cold space here. So we're not violating conservation of energy because you're taking the extra heat that wasn't your work from the cold space. So if we think about the second law, so we're going to be looking at a reversed heat engine. So from the second law, operating from cold to hot, which is exactly what you need for a heat engine type thing. And so work is done on the system to cause that to happen, because obviously the heat energy wants to go from hot to cold. So to go from cold to hot, we must be supplying work, which is what we can see happening in this question. So that's how we can link in the second law there. Alright, and that is this paper complete.